For decades, we've been chasing this dream of artificial general intelligence, right? AGI, an AI that can think and learn just like a human. But that whole chase brings up this huge, nagging question. How do we even know if we're getting any closer? How do you measure progress toward a goal as massive as true intelligence? Well, let's dive into a fascinating paper that proposes a brand new yardstick.
Okay, so first things first, we need a solid definition to work with. Researchers actually compiled a whole bunch of them, and they basically landed on this. Intelligence is really just an agent's ability to achieve its goals in a wide range of different environments. The key here isn't being the best at one single thing, it's about being good enough at, well, pretty much everything.
And this slide right here is a perfect way to visualize the problem with AI today. What we have is called narrow AI, and these systems are absolutely incredible at one specific, really complex task. Think of it like a tall, thin spike of ability. But the goal, AGI, is the total opposite. It's a broad, solid foundation. It's the ability to solve all the simple problems first, before you ever try to tackle the complex ones.
So, what this paper is really saying is, maybe we need to rethink our whole approach. Instead of building these super specialized, narrow spikes of ability, we need to fill the task cup from the bottom up. What that means is that real progress isn't measured by solving one more hard problem. It's measured by mastering that entire base layer of simple, general tasks first.
And this really gets to the core of the roadblock we've been hitting. You just can't build what you can't measure. For years, AGI research has felt a little bit like flying blind, Like we're in a cockpit with no dashboard to tell us if we're even heading in the right direction.
The author of this very paper, Arthur Franz, he absolutely nailed the issue way back in 2015. He said, one of the troubles of AGI research is the lack of a measure for partial progress. Without a way to measure that partial progress, how do you know if a new algorithm is a dead end or if it's a genuine step forward?
And the tests we have now, they just don't cut it. Take the famous Turing test. It's basically a pass-fail exam. It can't tell you if you're 10% of the way there or 50%. And a lot of algorithms that seem partially intelligent are really just those narrow spikes we talked about. They can't generalize their skills to new problems. We've been missing a true progress bar for AGI.
So, what's the big idea? Well, this paper proposes something pretty radical, but also incredibly elegant. It's all about reframing the very idea of intelligence around a core concept from information theory. And that concept is compression. The entire theory really builds from this one powerful idea.
The whole thing starts with this theory called universal induction. The core idea is actually pretty simple. To truly understand something, whether it's a sequence of numbers, a story, you name it, you have to be able to find the shortest, most compact explanation for it. It's all about finding that simple pattern that's hidden inside all the complexity.
So the crucial takeaway is this. If you can find the most compressed way to represent any piece of data, you have demonstrated true understanding. In this view, intelligence itself is the ultimate compression algorithm.
And what's so cool is how this connects a few really big ideas. It all starts with a classic philosophical principle we've all heard of, Occam's razor. The simplest explanation is probably the best one. Well, in computer science, that becomes something called Kolmogorov complexity. The shortest computer program that can generate a pattern shows the deepest understanding of that pattern. And here's the payoff. Once you have that short program, you can accurately predict what comes next. Simplicity leads directly to prediction power.
Okay, this is a really beautiful theory, right? But the big question is, can you actually test it? Can you build a benchmark based on this idea of simplicity? Well, the author designed a brilliant experiment to do exactly that. They basically created a gym for AGI. First, they systematically generated every single possible simple computer program, these things called Turing machines, with just 2 or 3 states. And you have to think of these as the absolute most basic computers imaginable. We're talking millions of programs for the 2-state machines and literally billions for the 3-state ones. Then they ran every single one and collected all the unique patterns of zeros and ones they spit out. And the result? A definitive, exhaustive test set of all simple computable problems. And the patterns they collected were all over the place. You had some that were incredibly simple, like just alternating ones and zeros. But you also had surprisingly complex ones, even from these tiny 2-state machines. And for the patterns from the 3-state machines, well, the underlying rule gets so intricate that, as the paper itself notes, it takes real human intelligence just to be able to spot it.
So this sets up the ultimate test. You've got this benchmark with thousands of these different sequences. The question is, could a brand new algorithm, one that's built on this principle of compression, just look at the output and work backward to find a short, simple program that creates it?
So, how'd it go? Did the algorithm actually work? This was really the moment of truth for this whole new way of measuring intelligence.
Okay, get ready for this. For the simplest class of problems, the results were, well, they were stunning. The algorithm successfully took every single one of the 210 unique sequences from those two-state machines and compressed it back into a small, elegant program. It didn't miss a single one. A perfect score.
And this wasn't just a one-hit wonder on the easy stuff. When they moved up to the much more complex sequences from the three-state machines, the algorithm still successfully compressed an incredible 80% of them. This proved the method wasn't a fluke. It was genuinely robust.
But here's the most important part, the real kicker. The algorithm wasn't just finding any program that worked. It was finding incredibly short programs. The average size was around 22 to 27 bits. That is almost exactly the theoretical minimum complexity of the original machines that created the patterns in the first place. In other words, it wasn't just finding an answer. It was finding the simplest possible explanation.
And this all leads to the paper's really powerful conclusion. The author speculates that the path forward to even greater intelligence, to solving even more complex problems, might not require new, complicated theories. It might just require a mere persistent application of this one core idea: compression. So this leaves us with a really provocative thought to chew on. We often think the path to AGI is all about bigger models and more data. But what if that's only part of the story? What if the true path is paved not with more, but with less? Not with more data, but with better, more fundamental compression? It's a question worth pondering.